Hi everyone, I am Ravimba Koranjai. I'm a PhD candidate in University of Houston. Today I want to talk about our work, SolMover, a smart contract code translation platform based on concepts, and our framework. This is a joint work with grant support from SUI Foundation, who builds the Move language, which we actually use in the paper, and also with my advisor Dr. Wedong Shi and my committee member Dr. Lei Zhu from Kent State. So first, let us start. What is a smart contract? So unlike the name, they are neither smart nor a contract. Smart contract is a programming language which you can actually write code in and deploy, and that actually powers Ethereum and other smart contract blockchain languages. So these blockchains functions actually have different things to do, and it can work in a different way. These smart contracts enable them to work. They are a programming language. They come with very strict safety preconditions which they have to adhere to because they are used in financial sectors, and they are immutable. So if we look at like how it works, for example, in Ethereum, every node contains a virtual machine similar to Java, and they're called EVM, and the code actually runs inside that. Most of the EVM compatible codes are written in a language called Solidity. So most of the smart contracts are written in Solidity, and they run inside the EVM that powers those blockchain. If we look at in a very high level, this is how it looks like. So a user uh, sends some data. There is a smart contract which executes in a very specific condition. It executes it, and the user gets the money back, or based on what that smart contract is supposed to do. Now, what is a SolMover? SolMover, in short, is Solidity to Move code translation platform. Why? Because smart contracts are unconventional programs. These are not like normal programming languages. They really do three things. So they define a new asset type, they read, write, and transfer those assets, and they check those access control policies for those asset. So we need a language which is safe and abstraction free, and which also has a very strong isolation. Now, we chose Move, which is based out of Rust, and encodes some of these properties. And one of the prime reason to choose Move was that here it cannot have very much bigger footprint in the whole available code repository. So one of the reason is that we have a lot of code already smart contract written in Solidity, but if we want to target a language, a low resource language, Move was the perfect candidate because this is a safe language, but these also have very strong encoding properties. But this is also not a language we can train a new large language model or a code translation platform, because in whole GitHub you will probably find roughly 1,000 code available in Move. So let's look at some of the intricacies of what Move enables, what Move has, what Move doesn't have. So for example, Move has the primitive types, Boolean. Move has unsigned integers. If you want to write something in Move, this is how you write. You define an integer field, you write a structure, you write another structure. Now, based on the reference and ownership, Move is based out of Rust, so it has Rust-like ownership semantics, but it is not exactly Rust. So most of the existing LLMs, if we want to use that, it starts producing code which looks like Move, but essentially is Rust code, which does not compile in Move because it doesn't understand the intricacies of Move. For example, it doesn't have no reference to references. like at the ampersand and t. So it also doesn't have, like, its struct and data structures cannot contain references, so no lifetime node reborrowing, which Rust has, and it has a much simple borrow checker as a result. Now coming to SolMover. So this is a whole overall architecture of our SolMover. So if you look at it, what does it have? It has the input code or input solidity contract. Then we go through certain stages where it learns from that contract what the contract actually does. Then how humans as us learn to code, it actually breaks it down based on concepts, which we'll go into a little bit later. uh, Breaks it down to different tasks, and it understands that what it actually does, and creates very small subtasks based out of that. That is done with two part of LLMs. So the first part is based out of part where we actually kind of understand the concepts. The second part actually generates that code based off each of those subtasks. It takes those subtasks and generates very small parts of code which get stitched together and goes through a iterative verification process. Now let's look at each part of this whole pipeline. So first we look at the concept mining part. So what essentially happens, these are like two parts which we'll go into. What happens is that first, we fine-tune the one of the LLM on move textbooks, white papers, tutorials to understand move concepts. Then we use retrieval augmented search to kind of build those concepts. So that is used to identify relevant move concept for a given Solidity code snippet. And then we generate the subtask based out of those concepts. So here, let's look at the first step, the concept mining. We define the query keywords as set x of x1, x2, x2, xk. A retrieval function denoted as r of xc to c operates on the query x and the retrieval database, which we call c. This function identifies and returns the most similar text fragment, which we call CS here, within the context C. Subsequently, a generative model G takes the retrieved fragment CS and the query context X as input. In the context of token level prediction, where the predicted sequence is restricted to a single token n is equal to 1, here G predicts the subsequent tokens denoted as Y, which is from xk plus 1 to xk plus n. So formally now we have py is the formalized sequence. Now, once we have the concepts, we go to subtask generation. So here, the concepts are built out of all the move text available, all the textbooks, all the codes that's available, and then once it identifies what it has to do, it creates very small subtasks which can be thought of very small code modules, but it does not produce code. The first LLM does not know how to produce code. It only knows to understand a Solidity contract and actually produce subtask. It doesn't even know if the subtask is going to be in move or whatever language, whatever it has been trained on, which for this paper, the move textbooks and the concepts, it creates these subtasks. Once we have this subtask, SolMover is our code translator or generator, which takes these subtasks generated by previous LLMs, uh, as we see, and generates the code in move. This is an instruction trained model based on Alpaca. Alpaca is an open source instruction following model trained on Llama model with 52,000 self-instruct dataset. And for our instrumentation part, we use LangChain for prompting, which takes each of the subtasks along with any code snippet example found and generates code using this fine-tuned model. This model has been fine-tuned on very small amount of whatever has been available move code, and it has been actually trained on very strict alignments to do not produce semantics which are of Rust. This generated response is then compiled into or stitched into a single file based on the task sequence which the LLM1 provides to rebuild the translated code for the original task. Now comes the verification part. This is now sent to move CLI for compilation. All the compilation errors are logged and added as memory to LangChain agent and sent back to SolMover for program verification. We run this process iteratively 5 times. If the candidate's response passes the compilation stage, we log it as successful. Otherwise, we do not log it. For our evaluation, here you can see how many codes we got as a successful translation. You will see on the other parts where we actually checked, you will see most of the other state of the art at the time when this paper was written. We have either non-compilable code for most of them. Even when it's compilable code, it has a mixed performance, which GPT 3.5 had. Now, if we look at actually code translation performance, you will see in successful translation, the total translation task, SolMover, the total translation task has been able to perform pretty remarkably on all of them, much more based out of GPT 3.5. If you look at the bug mitigation, where it actually takes faulty code and tries to mitigate bug on it, you will also see it has better performance. It also has incomplete translations, but it also has better translation after the feedback. Now, based on contract correctness, if you look at it, you will see after we get the feedback back from move prover, we see improvement, but it's a very negligible improvement. So we kind of look at that, okay, if the move prover actually formally did prove any quantifiable benefit to our framework. So in conclusion, we started with this 4 research questions. Can we use LLMs to learn coding concepts? And can the concepts be used to generate granular subtasks? Based on what we have empirically seen through our framework, we were able to empirically observe a successful code translation. However, we do not want to call them a concept, but rather contextual association. Also, can we generate code in a low resource language that the LLM have not been trained on? Yes, based on our results, we can confidently say that yes, it can be done using this framework. And also, can we mitigate bugs using compiler feedback? That we can also confidently say that yes, we were able to mitigate bugs based on that. For future tasks, we want to explore if we can use these methods for future other NLP tasks much in a bigger concept. Can we also generalize this on other domains out of code on other NLP tasks? And can we actually start generating low resource code such as move completely on its own without relying on code translation? Something we have kind of explored in one of our future work, which has been under review. Thank you. I would like to take any questions you might have. You can also read the whole paper if you follow that QR code. And if you want to get in touch with follow-up questions or any other queries, I'm happy to help. Thank you.